This is paper 1A of quiz 2. In this question 1, you need to do mesh analyze. So let's look at the circuit. Before we look at the circuit, I will put down the number on the device. First, I will put down the number next to the component. First, I will put down the number next to the component. First, I will put down the numerical value next to the component. E1, 10 volt. V2, 6 volt. R1, 2K. R2, 4K. R3, 1K. Next, we're going to analyze the circuit or the loop with mesh analyze. So we will use KVL on loop 1. We call this 1. We call this 2. You can use left or right, but you have to specify this very clearly. We can start from any component, and also we already have the direction of the loop, so we are using the clockwise direction. Again, if you reverse the direction as to the anti-clockwise, you will still get the same answer. First, this current here, the imaginary current I1, will enter E1. You can see here from the negative side. So we'll say this is minus 10. Again, do not put any unit, just minus 10. The prefix is important, but the unit will confuse you or is not necessary when you're solving a system of equations. Now, after it passes through the 10 volt, it passes through R1. Now, remember we need the voltage, and the voltage is equal to IR. Your I you don't know, but you know this is I1. So IR is the value of R1 multiply I1. And this become, and remember, for in this system, for any resistor, we use positive. So this become positive. I put the 2K before, and again, no need to put omega, just 2K. And then your unknown, which we are going to solve, is I1. Now here is the most tricky part. Your current passing through R3 from top to bottom, and this is I1. However, there's another current I2, which in the opposite side, it will go from the bottom to the top. So R3, there will be two current, one down, one up. But we are analyzing I1. So you have to, the rule, now this is a method, and this method work. This is what engineering do. Engineer invent or discover a method, it works. So this method say we are analyzing I1. So you push the I1, but there's some I2 here going up. So we have to make the I1 win this match. So it means the overall current passing through R3 in this loop must be I1 minus I2. So this become I1 minus I2. Okay. Now the value of R3 is 1K. So you put 1K here and the sign is positive. So this is our first equation. Now you expect that you're going to solve the equation for I1 and I2. So you can either just keep this one or you can just simplify the equation. It's up to you. So I just say 1. Next, you will apply KVL on loop 2. Okay, let's look at loop 2 here. We can start from anyone. Maybe I can start from the E2 first. If you look at loop 2 here, it enter E2 again from the negative side. So it means 6 volt here must be written is negative. Now remember, if another question, it reverse this one. In this case, you must change it to positive 6. So it really depends when the current enter the source, whether it is entering from the positive or from the negative side of the source. And we use this sign to determine the voltage. So we should put negative 6. The next component here, you can choose, of course. If we follow the path, the next component will be R3. Honestly, you can do R2 first, but let's do R3 following. Now I2 going up. Again, this time, from the point of view of I2, you must push the current up from the bottom to the top. But opposite side, there's an I1 counter it. So overall, the current, when you analyze the right hand side or the loop 2, I2 must bigger than I1. Now you may wonder which one is bigger eventually. Now remember, that's what engineering doing. You have to follow the rule and you don't need to worry about which one is actually bigger or which is the wheel direction. All you need is follow the rule. And the rule say, when you analyze I2 must bigger than I1. So it means you must change I2 minus I1. You are talking about R3. The value of R3 is 1K and the sign is positive. Can you see this is how I write down the equation step by step. Last, this loop here will enter R2 and the only one current, which is I2. So the potential is positive 4K I2. Positive 4K I2. That is your equation 2. These two equations, they are the key in this mesh analyze. You have to analyze or set up these two equations correctly. Otherwise, the rest will mess up the calculation. Now, the rest is mathematics. We want to solve I1 and I2. So let's follow the mathematics. I will say from I1 or from equation 1, we put this one to the right hand side. We find I1, 2K, 1K. So this become 3k I1. I2 is minus k I2, and this is 10. This is equation 3. From 2, we do the same thing. We first look at I1. This is 1k minus I1. So this has to be minus k I1. I2, again, this is 1k I2, and this is 4k I2. So they are both positive. So you will get plus 5k I2, and put the negative 6 to the right hand side. So it becomes positive 6. You can solve this system of equation by whatever method you know. Elimination, matrix, and all the methods, substitution. So what I will do here is I will do 3 plus 3 times 4. So when you operate this one, the first term here, this term is 0. Of course, this is my aim. My aim is to eliminate I1. So I find the equation 4 is negative, equation 3 is positive, so I add, and I have to scale the equation 4, so I will multiply 4 by 3. So when you add up these two equations, this term becomes 0. So you can find here, this is 3 times 5, so this is 15. 15 plus minus 1, so you become 14 k I2, and this is 18, 28, and so of course now I is equal to 28 multiplied 14k. The k here is simple. It means this is mini. 1 over k become mini, and this is 2 milliwatt ampere. This is how you use calculate the value with the way we can save the unnecessary complication. At the same time, we keep everything correct. So we have to add ampere here. Once we know the I2, we can substitute it back with either 3 or 4. So maybe we can do it with, say, 4. So we substitute I2 2MA into 4. So you have minus k I1 plus 5k I2 2m. Now again, you don't need the a here. You just keep the prefix m equal to 6. The beauty is here, the k, the m, k is 10 to the power 3, m, mini is 10 to the minus 3. So effectively, they sort of like a cancel out, and you have minus k I1 plus 10 equal to 6. So k I1 equal to 4, and I1 equal to 4 over k. It means 4 milliampere. So this is I1. Okay, once we find the I1 and I2, let's see what really happened. Now let's highlight again. I1 4, I2 2. So if you go back here, let's look at R3. The left hand side, or the loop 1, the current I1 pushing down. And now we know this is 4 milliamp. The opposite side, I2, pushing up, and this is 2 milliamp. So overall, the real physical current is going down. So the current passing through resistor 3 must equal to 4 mA minus 2 mA and equal to 2 mA. You must specify this is from top to bottom in this diagram. So this is actually our part B. So part B, I3 is, in this case, is I1 minus I2 because we know the magnitude. So this is 4 milliamp minus 2 milliamp is 2 milliamp. You must stay, this is from top to bottom. And the voltage, once you know the current, the voltage V is 3R3. So this is 2 milli. R3 is 1K ohm. So this is 1K. So this is 2. Remember, you're doing voltage. So this is volt. So this is the answer for question number 1 of paper 1A. Question number 2, paper 1A. You're allowed to choose either you use Thevenin equivalent circuit or Norton equivalent circuit to solve this problem. So both circuits, they are the same, and we'll see how to apply Thevenin and Norton equivalent circuit to solve to simplify this circuit. So let's do it. Number 2, use method 2. The first thing is use Thevenin theory to find the Thevenin voltage, okay, and the Thevenin resistance. So you must remember the procedure, how to do it. So let's redraw the diagram, okay. So if this is your volt, and this is R1 2K, and this is R2, which is 6K, R3 6K, RL 10K. So we first apply the theory. We can start finding the Thevenin voltage. So the Thevenin voltage, say you first remove RL. So once we remove this one, this is 2K, and this is 6K, and this is 6K. So this is, now we remove the RL, the load, and we want to say what is the voltage here. We call this Thevenin voltage. Now this voltage, we discussed this one in tutorial. I hope you remember the argument. This voltage is the same as finding the voltage at this point. This is an important point. And if this one is 0 and your source here is 12 volt, so this part here you must able to see is a potential divider. It means you must see it in your head. This is 12 volt. You withdraw this one, 2K. This is 6K. And you are effectively finding the Thevenin here, or we put some number here. A, B, between A, B is exactly between this one is also A. They're equivalent in terms of the voltage. So the Thevenin voltage TH is proportional to 12, and the proportional constant denominator, the sum, numerator depend on where you measure the voltage. You measure the voltage across the 6K resistor. So this is 6K. And you should find this one equal to 9 volt. So Thevenin voltage 9 volt. Here, to find the Thevenin resistance, we put this one here. Now this time we have to kill the source. We have a voltage source, so the rule to kill the voltage source is connected. So we have to withdraw this circuit. Instead of 12 volt, we just connect it using a straight line. Again, this is how engineering do things. They have a lot of rule and you have to remember it. This is 6K and this is 6K. Now you are trying to find the voltage across here. So this is, you're trying to find the resistance across this network. We call this Thevenin resistance. Now again, you must able to, in your head, to see this circuit is exactly this circuit. 6K. The reason is there's a two splitting point, this one and this one. So R1 and R2, they are actually connected in parallel in this sense. So this is the point here, and if we withdraw this one here, this will be your R1 2K, and this is your R2 6K. They recombine and do it here. So if we say this is A, B, this is also A, B. Now once you decided this one, this is easy. So the Thevenin resistance is 6K in series. So when you in series, you add the two resistors, which is 2K and 6K. So these two resistors, they are in parallel. So I put the parallel side here. Okay, so 6K you can use your calculator and find the value of 2k and 6k in parallel. So it's a 2 inverse plus 6 inverse equal inverse. So it's a 1.5. So this is 1.5k. So your overall is 7.5k ohm. Don't forget the unit. Okay, this is 9 volt. Beg your pardon. So now we got this one. What it means is we found Thevenin voltage, Thevenin resistance. So with these two, what we are saying is this circuit here can be reduced into this form. It means if you just focus on RL, the rest of the circuit can be replaced by this one. First, we have a source. Okay, positive, negative. This is your Thevenin voltage. Now remember, this is not 12 volt anymore. It's not 12. You must replace the 12 with the Thevenin voltage you just found, which is 9 volt. So this is your Thevenin voltage. And the first resistor here is your Thevenin resistor. This is what you find, 7.5k ohm. Now you put your load RL back to the circuit. So it means for the load, this is 10k ohm. So this circuit here is equivalent to your original circuit. So the next case, we done this one. Hence, use the current divider formula, find the current through and the voltage. Okay, so once you draw this one, it's easy. You can do it either way. You can do it from a different perspective. Say, for example, you can find the voltage first, and also there's no specific method as long as you find it. Say, I can find the voltage across RL. So this voltage we know is equal to 9 volt. Remember now the voltage source is 9 volt. And this is 7.5 plus 10. They're all K, so I just use the numerical value. This is 10. So what you will find here, you will find this is equal to 5.14 volt. And once you know the voltage, now you can know the current. There's a different method to find the current. You can find the sum. So the current passing through L, there's a two method. One is 9 volt and this one is 7.5k plus 10k ohm. So you will find this is equal to 0.514 milliamp, or alternatively, you just apply Ohm's law to here. So the Ohm's law say this is V over R, and this is 5.14 volt. R is 10k, so it's 0.514 milliampere. Just clear up here. Beg your pardon. We are still working on number 2. So we done this one, done this one. So the next one is, there's the same circuit. Can we solve all this one with the Norton theory instead of Thevenin? the answer is yes, we can still do it. Let's do this one here. And okay, next we're going to apply Q3 using the Norton equivalent circuit. So okay, again we have to redraw the circuit, and I use the same method, two different approach. The first one is find the Norton current. Now this time you have to bear in your mind what is the circuit will look like, the Norton one. Thevenin is we use the potential divider, replace the original. In Norton, we use current divider. So it means ultimately you want this happened. You want to say this RL for the RL as if there's a current source. This current source will split the current into two parts. The first part is your R Norton. The second part is your load. So this time we use a current divider instead of voltage divider. It divides the current into two paths. And from here we can find the voltage and the current passing through RL. So from this point of view, the Thevenin approach and the Norton approach, they are equivalent. Now we want to find this current source, therefore we call this I Norton. Okay, so this is our ultimate aim. Now therefore we have to find I Norton. Now Rn incidentally is the same as RTh. It means we can maybe do this one first. So this one is easy. We just do the same thing. Q the source. Okay, so we place the potential divider with a strict line. So your source become here, and this is 2K, and this is 6K, and this is 6K, and we want to find the resistance across this A, B. We call this R. In Thevenin, we call the Thevenin resistance. In Norton, we call the Norton resistance, and they're exactly the same. Now, if you watch the previous one, question 2, you should understand these two here, they are connected in parallel. So it means the Rn is again equal to 6K plus 2K parallel 6K, and you will find this is equal to 6K plus 1.5K, and this is 7.5K ohm. So we found the Norton resistor. Now to find the Norton current source will be a little bit complicated. So let's do it. So first we remove the RL, but this time it's slightly different. So let's do it. Plus minus, this is 12 volt. We still keep this one. This is 2K. This is 6K. And this is 6K. Now, the difference between Thevenin theorem and the Norton is, this time in Thevenin, if you go back here, you just open the source. Can you see it? You just open and find the voltage here. But this time we want to find the current, so we cannot just open it. It means this time we have to connect it. So this is important part. And we want to find not the voltage between the point, we want to find this current passing through here. And this current passing through here, we don't know yet, up or down, it doesn't matter. I just put a sign here. This is what we call I and Norton current. So how do you find this one? So this is like a simple circuit analysis now. How do you find the current passing through? This current is the same current passing through I N. So if you can see here, 12 volt will start a current. We call this one the total current or whatever. It can be equivalent or whatever. How about we call it equivalent? At this point, it's split into two parts. One is down, one is the Norton current we are trying to find. So this is I2, okay, the current passing through here. This one is exactly I3. You can call it I3 or you can call it IN. It doesn't matter as long as we know this is what we want to find. And the same here, we can call this I1 or I equivalent. Why I equivalent? Because we have to first find the total current coming out from the 12 volt source. Once you find the total current, we can use the current divider method and find the IN. So what I mean is, if you look at this circuit, it's easy now because IN must proportional, like a current divider, I equivalent. And the proportional constant denominator is 6K plus 6K. Now, remember the rule. If you want to find the current in this path, it's controlled by the resistor of the other path. But in this particular case, both resistors, they are equal. So you just put 6K here. Now the next question is, how can we find the total equivalent? Now if you find the total equivalent, you can redraw your circuit again. Can you see this circuit here? If we redraw it in this way, this is your 2K, and then it's split. This splitting point A is the splitting point A here, and the right hand side is your 6K, and this one is your 6K, and then you recombine. This is your B, you recombine this one here, and then you reconnect. So this is 12 volts. So this one here, put it here. We use a single resistor to get it. And this single resistor is equivalent. And this resistor here, R equivalent, is 2K plus 6K parallel 6K. And when the two resistors, they have the same value, they are connected in parallel, the equivalent is half. So I don't need to use calculator. This is 3K. So this is 5K. So this is 5K, and this is 12 volt. Don't lose track. So the total, this current coming out from the 12 volt, this is I equivalent must equal to 12 multiply 5k. So this is 2.4 milliamp. So we find this current. It means this current here, is 2.4 milliamp. Now we substitute this back here. 6k plus 6k, you see it's half. This is 2.4 milliamp. So this is equal to 1.2 milliamp. Okay, we put everything here. We know now the Norton current is equal to 1.2 milliamp. So let's withdraw, put the circuit back here. This Norton current is 1.2 milliamp. And the Norton resistance here is 7.5 kilo ohm. Our load is again is 10k, so this is 10k ohm. So everything is here now, and this is this current, and this is the current IL. This current, this is a current divider again, so it is proportional to IN, and the proportional constant, the denominator is the sum. Now remember, this time is the opposite branch. It's split into two branches. It's the 7.5k. It means is this resistor control how much current passing through the opposite branch. So IL equal to 7.5k, 17.5k, and this is 1.2 milliamp. And you will find this is equal to 0.514 milliamp. This is exactly the current we found in last question. Okay, voltage. The voltage across your load, of course, is IL, RL. This is 0.514 amp, and the R is 10k. Again, M and K, you can say sort of like a cancel. So it's a 5.14 volt. This is exactly the same value we found in question 2. Okay, so I hope you can see what the two methods, they will lead to the same answer, but the approach will be slightly different. The key lesson I want to learn is drawing step by step, understand what you're going to do. In terms of the mathematics, there's not much. All you need is the equation for potential divider, the equation for current divider, of course, Ohm's law.